All right, guys, let's go ahead and get started here with our first problem. It says an object with a mass of 86 kilograms, so I'm going to highlight this part, is being pushed to the right with a force of 171 newtons. Being pushed to the right is talking about an applied force. The coefficient of friction between the object and the ground is 0.2, so this is talking about my coefficient. First thing it wants us to do is figure out what the normal force of the object is. Well, before we do that, let's just go ahead and draw a free body diagram. So here's our object. We know that we have gravity pulling down on this object because gravity is always present. We have force normal pushing up on the object. These two are the exact same size because the object is not accelerating up or down. And then we know that we're pushing it to the right. So I'm going to go ahead and draw that force applied to the right. I see that force applied over here. And then to the left, we have force friction. I'm going to draw that force friction here. I'm not going to make these the same size just because I have an idea that they're going to be unbalanced, but we'll confirm that later on. Now that we have all of our forces drawn in our free body diagram, let's go ahead and solve for the normal force. Well, like we said, normal force is the same size as force gravity. So we're going to solve using the equation for force gravity. Therefore, we get force gravity is equal to mass times gravity. So I find out that my normal force is just equal to 86, because that's my mass, times 9.8. That gives me a normal force of 842.8 newtons. Now that we know our normal force, we can move on to the next one. Next one says, what is the object's force of friction? Well, force friction we solve by using this equation. Force friction is equal to force normal times mu. We know what mu is, it's right here. We know what force normal is, we just solve for it. So this is pretty easy. We just plug in our numbers. We get force friction equals 842.8 times 0.2. Find out that force friction should be 168.56 newtons. And then our last part says, what is the net force acting on this object? Well, net force, we know, is equal to the forces that point to the right, so force applied, minus the forces that point to the left, force friction. Or it's also equal to mass times acceleration. We know the mass in this problem, but we don't know the acceleration, so we can't use this part. So we're going to go ahead and use this to solve for the net force. We find out that net force is equal to 171, because that's our force applied, minus 168.56, because that's our force friction. And I'll just write these up here as well. We solve by just adding these together, and we find out that the net force acting on this object should be 2.44 newtons. All right, guys, so let's take a look at our next problem here. It says a 57 kilogram object is pushed with a constant velocity across a rough surface with a force of 56 newtons. So key word here is constant velocity. It's also important that it's a rough surface. That's telling us that there's some sort of force friction present in this problem. And we see that it's being pushed with a force of 56 newtons, talking about an applied force here. So the first question says, what is the object's net force in the x direction? Well, if we were paying attention to the problem, we see that it's moving at a constant velocity. Because it's moving at a constant velocity, that's going to mean that forces are balanced here. And because they're balanced, that's going to mean that the net force in the x direction is actually just 0 newtons. Again, how do we know it's 0 newtons? Well, we know that net force is equal to mass times acceleration. A constant velocity means that acceleration is equal to 0. If acceleration is 0, that means that our net force is 0. All right, next it says, what is the object's force of friction? So force friction, we know we can find out by taking our force normal and multiplying it by our coefficient of friction. We don't have the coefficient of friction right now, and we don't know force normal either, so we can't figure out what force friction is at the moment. There's too many unknowns. But what we do know is that our object's moving at a constant velocity, and it means that our forces are balanced. So let's go ahead and draw this free body diagram really quick, and maybe we'll make this more apparent as to what the force friction is. We have force gravity pointed down on this object. We have force normal pointed up. These two are the same size. How do we know that they're the same size? Because this box is not accelerating up or down. Next, we have force applied, which it told us in the problem is 56 newtons. And then we also have force friction coming back on it. So I'm going to make force friction the same size. And the reason why I'm doing that is because it's telling me that it's moving at a constant velocity here. So these forces in the x direction are balanced. So force friction and force applied are the same size. Therefore, when this question asks, what is the object's force of friction? Well, the force friction is just equal to the force applied. And we can see up here in the problem that the force applied is 56 newtons, so force friction is just 56 newtons. Another way to figure this out is just to write our equation like we would before. Net force in the x is equal to the forces that point to the right, force applied, minus the forces that point to the left, force friction. We know net force is 0, so we just get 0 equals force applied minus force friction. We solve for force friction like we did up here, and we just find out exactly what we did here. Force friction is equal to force applied. We plug in 56 for force applied, and we get 56 for force friction. All right, our next one says, what is the coefficient of friction between the objects? Well, I wrote that equation right here, and we're going to go ahead and use it right now. Force friction is equal to force normal times the coefficient. Go ahead and divide force normal over so that I get the coefficient by itself now. And I find out that the coefficient of friction should be equal to force friction over force normal. We know what force friction is, we just solve for it right here. Force normal, though, we can look at our free body diagram and see that force gravity is equal to force normal. So in this case, force normal is actually just equal to mass times gravity. The mass of the box is right here, 57 kilograms. So force normal just equals 57 times 9.8. That gives us a force normal of 558.6. Go ahead and plug this into our equation. We get mu is equal to 56 over 558.6. And that tells us that mu is equal to 0.1. And it's just 0.1. Mu does not have units. Okay, let's take a look at our third problem here. It says an object slides to a stop from an initial velocity of 17 meters per second over the course of 4.533 seconds. The object has a mass of 10.5 kilograms. So the initial velocity here is 17 meters per second. It does that in 4.533 seconds, so that's how long it takes. And it says that it comes to a stop, so that's talking about the final velocity, and a stop is referring to a final velocity of 0 meters per second. The object's mass, 10.5 kilograms. Awesome. So now that we've labeled everything in the problem, let's see what it's asking us to do. It says, what is the acceleration of the box? Hint, should this answer be positive or negative? Well, it's slowing down, so we know it's going to be negative here because our object's moving at some initial velocity and it's stopped at the end. So to figure out the acceleration, we're going to go ahead and use one of our kinematic equations. And we're going to use a little puff because we have VF, we have VO, we have T, and we're solving for A. So I'll go ahead and write that equation. VF equals VO plus A times T. Plug in my numbers. VF is 0, VO is 17, A is unknown, and T is 4.533. Now we'll go ahead and solve by subtracting 17 over and then divide by 4.533. We find out that acceleration is equal to negative 3.75 meters per second squared. Next, it says, what is the net force on the box in the x direction? Well, net force, we know, is just equal to mass times acceleration. We know the mass, it's right here in our problem, and we just solve for the acceleration. For this one, we just plug in the numbers, and it should be pretty easy. Net force is equal to the mass, which we said was 10.5, times the acceleration that we just solved for, which is negative 3.75. Go ahead and multiply that out. We get net force is equal to negative 39.34 newtons. The next question is asking us what's the force of friction on the object. We notice that it says that it slides to a stop. So if we were to draw the free body diagram of this box right here as it's coming to this stop, we would have normal pointed up because there's a surface. We'd have force gravity pointed down, and then we'd have friction acting in the opposite direction. We're going to notice that there's no force pulling it to the right because nothing's applying a force to the right in this problem. It's just sliding to a stop. If we write our net force equation, we see net force is equal to the forces that point to the right, in this case 0, minus force friction. So if we plug in our numbers, we get negative 39.34 is equal to negative force friction. That just tells us that force friction is equal to 39.34 newtons. All right, now our last one says the coefficient of friction between the object and the ground is blank. To figure that out, let's use our force friction equation. Force friction is equal to force normal times mu. If we're solving for the coefficient, let's just go ahead and divide force normal out to the other side. So we get mu is equal to force friction divided by force normal. We don't know exactly what force normal is, but we know that force normal and force gravity are balancing each other out. So force normal is going to be equal to force gravity, just like it was in our last problem. So force normal equals mass times gravity. So if we solve for that, we get force normal equals 10.5 times 9.8. That gives us a force normal of 102.9. Now we go ahead and plug our numbers in over here. We get 39.34 divided by 102.9. That gives us a coefficient of 0.38. And again, no units here because mu is unitless. Let's go ahead and look at our next problem here. And it says a 7.5 kilogram box is at rest on a table. The static friction coefficient, mu s, between the box and the table is 0.5, and the kinetic friction coefficient, mu k, is 0.15. Then a 1,910 Newton horizontal force is applied to that box. So I'm going to go ahead and draw a free body diagram of this box first before I get started. So here's my box. Now I'm going to go ahead and label my forces. I have force gravity pointed down on this box. I have force normal pointed up on this box. Notice how these two are the same size because I know that my box is not accelerating up or down. Next, I have this giant horizontal force being applied to it, and then some friction force coming back on it. First thing says, what is the normal force acting on this box? Well, we just said here in our free body diagram that normal is equal to force gravity because it's on a flat surface and because it's not accelerating up or down. So therefore, our normal force is just mass times gravity. The mass of the box is 7.5 and gravity is 9.8. That gives us a force normal of 73.5 newtons. Next one says, what is the maximum static force of friction acting on the box? So static friction is the friction that prevents an object from moving. So in order to find the maximum static force of friction, we're going to use our equation just like we normally would. We got force normal, but this time it's times the coefficient of static friction. So that's the only difference in the equation here, is that we're multiplying times the coefficient of static friction. The other thing to note about this equation is that force friction is actually less than or equal to this amount. So it can be this, but it also can't be any bigger than this too. And you'll see what I mean later on in the next problem. So if we go ahead and solve here, we get force friction, in this case, is equal to 73.5 times 0.5. So I get a force friction, or a force static friction in this case, of 36.75. And since it's a force, I'm going to say newtons. The important thing to note here is that this force of static friction is much smaller than this applied force, so therefore the box is going to start to move. So I'll go ahead and I'll write that because I think it's super important that the force applied is greater than the force of the static friction. And because it's bigger, it means that the box will move. Number 3 says, what is the kinetic friction? Well, since we know that the box is moving, we just do the same equation now, except we swap it out with our other coefficient. So we get force friction of kinetic is equal to force normal times that kinetic coefficient. And this is super easy because we just did it above, but basically it's just 73.5 again times 0.15. So we find out that our force of kinetic friction, because kinetic is in motion, is equal to 11.03. And again, that's newtons because it's a force. Number 4 says, is this box moving? Yes, the box is moving. And like we said before, it's because force applied is greater than that force of static friction, so the box will move. In other words, there's enough force to overcome friction, therefore the box will begin moving. Number 5 says, what is the net force on the object? So net force we know is equal to the forces that point to the right, force applied, minus the forces that point to the left. It's also equal to mass times acceleration, but we don't know the acceleration, so we're going to have to use this part of the equation to figure it out. So if we go ahead and plug in, we find out that our force applied, which is given to us, is 1910 newtons, minus force friction. Since it's experiencing acceleration here, we're going to use the kinetic friction, and that's 11.03. Now we just go ahead and add those together, and we find out that our net force should be equal to 1,898.97 newtons. And again, the reason why we're using the kinetic friction here is because we know that the box is moving, So we're finding out that net force when the box is moving. Number 6 says, with what rate does the object accelerate? Now that we know the net force, that's super easy to figure out. Net force is just equal to mass times acceleration. So we're going to take our net force and just divide by mass to figure it out. So we find out that acceleration is just equal to 1,898.97 divided by our mass, which was 7.5. Go ahead and solve for that real quick, and we find out that acceleration should be equal to 253.2 meters per second squared. Pretty big acceleration here, but it makes sense because we have a pretty big force. Number 7, if the object starts from rest, how fast will it be traveling after 5 seconds? Sounds like a job for kinematics. So we're going to go ahead and figure that out. And to do that, we're going to use little pup. So little pup says VF equals VO plus A times T. The T is right here in the problem, 5 seconds. The VO is 0 because the object initially starts at rest. And we're just solving for VF. We get VF is equal to A, which is 253.2, times our time, which is 5. We find out that VF should just be equal to 1,266 meters per second. Last part, and then we're almost done, says how far will it slide in that time? Well, how far is talking about the final distance. So let's go ahead and use big dog for this. Big dog is df equals do plus vot plus 1/2 at squared. We know the initial velocity is 0, so that's 0. We know the initial distance is 0, so that's 0. So we're just left with df equals 1/2 acceleration, which we know is 253.2 times t squared. T is 5, 5 squared is 25. Now we just multiply all those numbers together and solve and find out that the final distance is 3,165 meters. Let's take a look at one of our harder problems now. This one says a 10 kilogram box is at rest on a table. The static friction coefficient mu s between the box and the table is 0.3, and the kinetic friction coefficient is 0.09. A 3.5 Newton horizontal force is applied to that box. So let's go ahead and draw our free body diagram just like we would before. So here's our box, it's on a table, and now let's label the forces. We know we have force gravity pulling down on this box. Because it's flat on the table, we're going to have force normal pointing up on the box. We have a horizontal force acting on it, so an applied force, and then we have friction pulling it back. We don't know the exact sizes of this because it's not like our last problem where that force was ginormous. In this case, this applied force is actually pretty small. So I'm going to keep these arrows around the same size. Number 1 says, what is the normal force acting on the box? We know that the box is not accelerating up or down, so we can say, just like we did before, that force gravity is just equal to force normal. And if we know that's the case, then force normal is just equal to mass times gravity, which we know the mass is 10, and gravity for this problem is 9.8 because we're on Earth just like all of our other problems. So we find out that force normal is just equal to 98 newtons here. Number 2 says, what is the maximum static force of friction acting on the box? So this is where things get tricky. And let's take a look at this. You can figure out exactly what I mean. So force friction, we said in the last problem, or force static friction, like we said in the last problem, is technically less than or equal to force normal times the coefficient of static friction. So let's go ahead and plug these in and see if you can really understand what I'm saying here. So we find out that force friction, if we plug in our numbers, is less than or equal to 98 times 0.3. So that would give me a force of static friction that is 29.4 newtons. But this doesn't make any sense. And the reason why it doesn't make any sense for our answer is because we can see up here that we're only applying a force of 3.5 newtons. We can't have more friction than the applied force if the object's at rest. That makes absolutely no sense. So this is where this part of the equation is going to come in handy. This is telling us that 29.4 newtons is the amount of force needed to get this object moving. Unfortunately, we're only supplying 3.5 newtons. So what does that mean? Well, it means a lot of things. And the first thing it means is that this box is not moving. And why isn't it moving? Because we don't have enough force to overcome static friction. So I'm going to go ahead and write that here, saying force applied is less than the force of static friction. And since this is the case, the box will not move. Therefore, the value of our force of static friction is actually just going to be equal to that 3.5 newtons. And the reason being, our static friction doesn't need to be 29.4 newtons in order to stop this box from moving. It only needs to be 3.5 newtons because static friction has a ceiling, and that ceiling is at 29.4. But since we're only applying 3.5 newtons of force, we don't need all of this static friction to stop the box. We need just a little bit. Think about if you guys have ever tried to push something or move something. You might push it like kind of hard and you notice it's not really going anywhere. And then you try pushing it even harder and it's still not moving. That's a perfect example of static friction. How sometimes static friction can just be a small value like 3.5 and still prevent an object from moving. But other times it's got to be a way bigger value like 30 in order to prevent that object from moving. So this actually makes the rest of our problem super easy. And number 3 says, what is the kinetic force of friction acting on the box? Well, the box isn't moving. So since it's not moving, there's no kinetic friction. So this is just 0 newtons. And now, like we said before, box isn't moving. What's the net force on the box? Well, it's not moving. So because it's not moving, it's 0 newtons. With what rate does the object accelerate? It's not moving, so it's not accelerating. 0 meters per second squared. If the object starts from rest, how fast will it be traveling after 5 seconds? Well, it's not moving, so it's still 0 meters per second because it doesn't matter. The box is not moving. Number 7 is 0 meters per second. Number 8, same thing. How far will it slide? It won't slide anywhere because you guessed it, it's not moving. All right. It's not going anywhere. It's like the guy from the Wolf of Wall Street. It's not leaving. All right, that box is staying still no matter what you do. So this question actually ended up being a whole lot easier than I think we thought it was going to be. Alrighty, we have finally made it to our last problem here. So let's go ahead and check it out. It says a 20 kilogram box is at rest on a table. Assume it takes 137.2 newtons of horizontal force for the box to begin moving. Once the object starts moving, there is an acceleration of 4.116 meters per second squared. So let's go ahead and draw that box real quick. So here's our box, here's our table. Now let's start labeling our forces on this box. I have force gravity pointed down on the box. I see it's flat on a table, so I have force normal pointed up. I have a force applied pointed to the right, and then I'm going to have a force friction pointed back to left. In this case, though, I know that force friction is smaller than force applied, and the reason why I know that is because my box is accelerating. Because it's accelerating, there's unbalanced forces, and it's a positive acceleration. So because it's a positive acceleration, that's going to mean that force applied is greater than force friction. All right, let's get started with number 1. What is the net force on the object? So this is pretty easy. Net force is just equal to mass times acceleration. We know the mass, it's right here in our problem, 20, and we know the acceleration, it's right there as well, 4.116. Go ahead and multiply those two together. We get 20 times 4.116. We find out that the net force acting on our object should be 82.32 newtons. All right, number 2, what is the normal force acting on the object? Well, if we look at our free body diagram, we notice that normal and gravity are equal to each other again because it's on a flat surface and we're not pushing this box up or down. Therefore, force normal is just equal to force gravity, which is really just equal to mass times gravity. So we know that the mass of our object is 20 and gravity is 9.8. That's going to tell us that force normal is just equal to 196 newtons. Okay, 2 down, 4 more to go. What is the maximum static force of friction acting on the box? So this question is kind of tricky, and the reason being is that the force of static friction, we're usually used to it equaling force normal times the static coefficient. We don't know the static coefficient at the moment, so we can't really solve for it this way. But there is another way that we can solve for it, and that's by looking carefully at our problem. If we notice here, it says assume it takes 137.2 newtons of horizontal force for the box to begin moving. What does that mean? That means that we need to overcome 137.2 newtons of force to move this box. This is really just talking about the maximum static force of friction. So in this case, the static force of friction is actually just equal to that 137.2 newtons. And again, the reason why that's the case is because 137.2 newtons is the force needed to start moving the box. In other words, it's the force needed to overcome that static friction. Number four, what is the static coefficient? Well, that's easy. We just plug it into this equation and solve for the static coefficient. So we know that the static coefficient is just equal to force friction divided by force normal. Go ahead and plug my numbers in really quick. I get the static coefficient is equal to 137.2 divided by 196. That gives me a static coefficient of 0.7. Again, no units here, just 0.7. Number five, what is the kinetic force of friction? Well, to figure this one out, we're going to need to take our net force. And we know that the net force in the x direction is going to be equal to the forces that point to the right minus the forces that point to the left. So let's move some things around. I'm going to go ahead and add force friction over and subtract net force. I get force friction is equal to force applied minus the net force in the x direction. I know force applied. It's giving me my problem. I know net force. I just solve for it. So this is just going to be an easy algebra question. Force applied is 137.2 minus the net force, which is 82.32. Go ahead and add those two together or subtract, whatever way you want to say it. And we get force friction. And again, that is the kinetic friction is equal to 54.88 newtons. All right, last one. What is the kinetic coefficient of friction? We're just going to use the same equation we did for the static coefficient of friction, except we're going to change this little subscript s out for a subscript k. We get the kinetic coefficient is equal to force friction divided by force normal. Force friction has changed to 54.88. Force normal is still 196. So we divide those two and we find out that the kinetic coefficient of friction is equal to 0.28. Again, no units because the coefficient of friction is unitless.